You know when you reach for a metal doorknob in the middle of winter, and there's almost always that like split second of hesitation.
Oh, absolutely. You just know it's coming.
Right, you get that little involuntary flinch because you know deep down you might get zapped. And in that moment, it feels entirely random, like the universe just decided to play a tiny, painful prank on your fingertip.
Yeah, it really does. It feels like magic, or, I mean, just bad luck. But of course, it isn't random at all. What you are experiencing in that split second is a perfect mathematical certainty playing out.
Which is wild to think about.
It is. We like to think of electricity as this untamed, chaotic force, but it is bound by incredibly strict, invisible laws, laws that operate the exact same way every single time.
And that is exactly what we're going to explore today.
Welcome back to another deep dive. Today, we are taking a fascinating look at the invisible rules that dictate that doorknob flinch.
Yeah, and we're going to trace those rules all the way up to the macroscopic world. Exactly. All the way to the microscopic grid powering the smartphone or computer you are listening on right now. Our mission today is to look at the absolute foundation of electrostatics and circuit systems. Not to just memorize textbook definitions, but to extract the hidden mechanisms that govern basically everything in our modern lives.
Right, because by the end of this deep dive, you won't just be familiar with the concepts, you are going to understand the actual underlying physics. You will see how the exact same atomic mechanisms are at play in a balloon sticking to a wall and, the complex infrastructure powering a major city.
Okay, let's unpack this.
Yeah.
Before we can build a complex circuit or power a machine, we have to start at the absolute foundation, right? Yeah. We need to understand the raw materials of electricity.
We do, and that means starting with electrostatics, which is essentially the study of electrical charges at rest.
Just sitting there, waiting.
Exactly. And anytime you dive into the behavior of charges, you immediately crash into Coulomb's law.
Right, Coulomb's law.
It is the bedrock. Qualitatively, it tells us something most of us intuitively grasp, which is that opposite charges attract and like charges repel.
Sure.
But quantitatively, it provides the mathematical model to calculate the exact force of that interaction.
So when I look at the mechanics of Coulomb's law, it immediately reminds me of gravity.
Oh, that's a really good comparison.
Yeah, it seems like the exact same concept, right? Where the distance between two objects and the amount of stuff, or in this case, charge, they have dictates exactly how hard they push or pull each other.
What's fascinating here is that the mathematical structure is strikingly similar to Newton's law of universal gravitation. Both are inverse square laws.
Okay, inverse square, meaning distance plays a huge role.
Huge! If you double the distance between two charged objects, the force drops to a quarter of what it was. So these fields drop off incredibly fast, but when they are close, the forces are immense.
Which makes sense. The closer you get to the doorknob, the more intense the interaction until a snap. You get shocked.
Yeah. Right. But there is a massive fundamental difference in how gravity and Coulomb's law operate in the real world. Gravity only attracts. It only pulls things together.
Oh, right. Gravity never pushes you away from the Earth.
Exactly. But Coulomb's law introduces repulsion, and that repulsive force is wildly powerful.
Well, that makes total sense. But before we get to the spark itself, I want to talk about where these charges actually come from, because there is a fundamental concept here regarding the conservation of charge.
Yes, a very important concept.
And I have to admit, I get tripped up on this. We say things like, we're generating electricity, or we complain that our phone battery died or ran out of charge.
We say that all the time, yeah.
But if the conservation of charge is an absolute law, we aren't actually creating or destroying anything, right? We're just endlessly rearranging the furniture in cosmic electrified room.
That is a crucial distinction, and it honestly causes a lot of confusion.
Right.
Let's clarify the phone battery scenario, because it's a perfect example.
Please do.
When your phone battery dies, it hasn't actually lost its electrical charge.
Wait, really? Really? Every single electron that was in the battery when it was fully charged is still physically inside that battery.
Then why does my screen go black? Where did the juice go?
What you lost wasn't the charge, you lost the energy. Specifically, the potential difference.
Okay, I'm trying to picture this.
Think of a battery like a room where you've shoved all the electrons to one side.
Okay.
They hate being next to each other.
Yeah.
That's Coulomb's law in action, right? Like charges repel. They desperately want to spread out.
So they're packed in there under pressure.
Exactly. When you turn on your phone, you give them a pathway to rush to the other side of the room to achieve balance. And as they rush across, They power your phone.
Ah, I see.
When the battery is dead, it just means the electrons are now evenly distributed, they are relaxed. The total charge of the system hasn't changed by a single decimal point.
So you cannot create a net electrical charge out of nothing. No, you cannot. And you cannot destroy it. You just move the cosmic furniture around to create an imbalance and then harvest the energy as the universe tries to balance it back out.
Wow. So when I rub my shoes on the carpet, I'm not creating the shock out of thin air. I'm just physically, forcibly moving electrons from the carpet to my shoes.
Exactly. You are disrupting the balance. And because the universe prefers equilibrium, those electrons are going to jump to the first conductive thing you touch.
Like a metal doorknob.
Exactly, to disperse.
Which perfectly transitions us to the next massive piece of this puzzle.
Mm-hmm.
Because the law of conservation tells us we can't create or destroy charge, the natural next step is to look at exactly how we force these existing charges to move.
Right. How do we accumulate them on objects in the real world?
Yeah. How do we create those imbalances on purpose? And the source text outlines three main mechanisms for this, which are friction, conduction, and induction.
Right. And to really understand these, we have to look closely at the atomic level. It isn't just about things touching. It's about how tightly different materials hold on to their electrons.
Okay, let's look at friction first. The classic example is rubbing a balloon on your hair. We've all done it.
A staple of childhood science, yeah.
But what is actually happening there? Why does rubbing two things together cause a charge imbalance?
It comes down to something called electron affinity.
Electron affinity.
Right. Different materials have different levels of attraction to their outer electrons. Human hair has a relatively weak grip on its electrons.
Okay.
Rubber, which the balloon is made of, has a very strong grip. So when you physically rub them together, you are bringing their atoms into extremely close contact.
And the rubber just takes them.
The rubber literally strips the loosely held electrons away from the hair atoms. The friction is really just providing the mechanical energy to bring the surfaces together and pull them apart.
So the balloon becomes negative because it stole the electrons.
Yep.
And your hair becomes positive because it lost them. And because, charges repel, every individual strand of your hair tries to get as far away from every other strand as possible.
Which is exactly why your hair stands straight up.
That makes so much sense. Okay, so that's friction. But conduction is slightly different, right?
Yeah, conduction requires a conductive material, usually a metal. In a metal, the atoms are arranged in a lattice and their outer electrons are completely detached.
Detached.
Yeah, they form what we call a sea of electrons. They're just free to drift around the metal.
So conduction is just those free-floating electrons rushing across a physical bridge when two objects touch.
Basically, yes.
Like when I have a surplus of negative charge on my hand from the carpet and I high-five my friend, the electrons just flood across our skin to balance out.
Yes, exactly. Direct physical contact. The charge conducts across the barrier because the electrons physically migrate from one person to the other.
Ouch. Okay, but then we hit this third mechanism, which is induction. And this is where things start to feel like actual sorcery to me.
It is a bit counterintuitive, yeah.
How exactly does induction work? Because you are charging an object without even touching it. It essentially feels like, I don't know, electromagnetic peer pressure from a distance.
Electromagnetic peer pressure. I love that. That is actually a great way to visualize the invisible fields at play. Let's break down the mechanism.
Please do.
Induction is just Coulomb's law operating across empty space. Remember those free-floating electrons in a metal we just talked about?
The sea of electrons, yeah.
Right. Imagine you have a neutral metal sphere sitting on an insulated stand. It has equal amounts of positive and negative charges.
Okay, perfectly balanced.
Now, you bring a heavily negatively charged rod very close to the sphere, but you don't let them touch. Because the sphere is metal, its electrons are free to move. So what does Coulomb's law dictate?
Well, the intense negative charge on the rod is going to repel the negative electrons in the sphere. They're going to flee.
Precisely. The electrons in the metal sphere feel that intense negative pressure, and they run as far away as they can. They push all the way to the far side of the sphere.
Oh, I see.
So the side of the sphere closest to the rod is now largely positive because the electrons vacated the area.
Right.
Now, the sphere overall is still technically neutral. The electrons are still trapped inside it. They're just huddled on one side. But here is the trick.
What's the trick?
What if you attach a conductive wire to the far side of that sphere where all the electrons are huddled and run that wire into the earth?
Oh, wow. You give them an escape route.
Exactly.
The electrons are trying to get away from the rod, so they just take the wire right into the ground and leave the sphere entirely.
Exactly. They evacuate,
Huh?
and then you cut the wire. Then you pull the charged rod away. What are you left with?
You're left with a sphere that is missing a bunch of its electrons, so it's now positively charged.
Mm,
And you never even touched it with a rod.
exactly. You manipulated it entirely through field pressure.
That is just brilliant.
And if we connect this to the bigger picture, this isn't just a clever physics trick. This precise mechanism of moving electrons via shifting magnetic and electric fields without physical contact, that is the foundation of wireless charging for your phone.
Wait, really?
Yeah, and it is the exact basis of induction cooktops in modern kitchens.
That is wild. Okay, so up to this point, we've only been talking about static charges, things building up, sitting still, creating tension. But we need to make a massive leap here.
We do.
If we want to actually power the modern world, we have to transition from static, resting charges to controlled, continuous flow,
You just
which brings us out of electrostatics and into the complex architecture of electric circuit systems.
This is where we harness the tension. We aren't just building up a charge on a metal sphere anymore. We are creating a continuous looping pathway for those electrons to move and do continuous work.
And when we dive into circuit systems, we hit 4 major concepts that are inextricably linked: voltage, current, resistance, and power.
The big four.
Right. And I want to ditch the textbook definitions here. A lot of people try to explain this using water pipes. Voltage is pressure, current is the water.
Yeah, that's the standard analogy.
But let's try something more visceral. What if we look at a circuit, like a massive, sold-out rock concert?
Oh, I like that.
Oh.
Let's push that concert analogy and see how it maps to the physical reality of a circuit.
Okay, so the battery or the power source is the parking lot, and the concert stage is where everyone wants to go. Voltage is the excitement. It's the absolute desperation of the crowd outside trying to squeeze their way into the arena. It's the pressure.
Okay, I follow.
Current is the actual flow rate, the sheer number of people physically walking through the doors every single second. And resistance is the security checkpoints, the turnstiles, the narrow hallways that physically slow down the flow of people.
That maps brilliantly. Voltage is the electropressure, measured in volts. Without the excitement of the crowd, nobody moves.
Right, they just stand there.
Exactly. Current, measured in amps, is the volume of electrons actually flowing past a point. And resistance, measured in ohms, is the physical restriction to that flow.
So the turnstiles.
Yes. But let's look at why resistance actually happens at the atomic level, because this explains how the world works.
Yeah, what is the physical turnstile actually doing to the electrons?
Well, in a wire, an electron is accelerating because of the voltage, the pressure is pushing it. But a wire isn't an empty tube. It is a dense forest of vibrating atoms.
Okay.
As the electron speeds up, it crashes into one of these atoms, it bounces off, losing some of its kinetic energy, then it accelerates again and crashes again. It is essentially a microscopic game of pinball.
And when things crash, energy is transferred.
Exactly. The electron transfers its kinetic energy to the atom, making the atom vibrate faster. And atomic vibration is just another word for heat.
Oh, wow.
This is why resistance generates heat. This is exactly why your laptop gets hot when it works hard. It is literally the friction of billions of electrons crashing through an atomic obstacle course.
That makes perfect sense.
In an old incandescent light bulb, the resistance is intentionally made so high that the filament gets so hot it violently glows.
It brings us directly to the fourth concept, which is power.
Right.
If resistance is the electrons crashing into turnstiles and generating heat or light, is power just the measurement of all that chaos?
Essentially, yes. Power is the rate at which electrical energy is transformed into another type of energy, like heat, light, or mechanical motion.
Got it.
In your concert analogy, power is the actual measurable noise, the heat of the bodies, the work being done by the crowd once they get through the gates. And because all these things are connected mathematically, you cannot change one without affecting the others.
Right, because if you increase the resistance, say you close half the security gates at the concert, but the crowd's excitement or the voltage stays the exact same, the flow of people, the current absolutely has to drop.
And if the current drops, the total power drops. The music gets quieter, the bulb gets dimmer.
It's all connected.
It is. This delicate mathematical balance allows engineers to calculate exactly how much resistance a microscopic wire needs to safely deliver the perfect amount of power to a microchip without melting it.
Which honestly blows my mind when you consider how many tiny components are inside a single device.
It's a marvel of engineering.
But that introduces the final massive hurdle in understanding circuits. We've defined the basic behaviors: voltage, current, resistance. But how you arrange these components completely transforms the physics of the entire system.
Right. We are talking about circuit architecture,
Yeah.
specifically series, parallel, and compound circuits.
Exactly. And instead of looking at these as abstract diagrams, what if we visualize the flow of electrons like a massive ski resort?
Okay, I see where this is going. How does voltage map to a mountain?
Well, voltage is the potential difference, right? The energy pushing you from high to low.
Yes.
So at a ski resort, voltage is the physical elevation of the mountain.
Yeah.
You take the ski lift to the summit, and gravity or voltage wants to pull you all the way down to the lodge at the bottom. The current is the actual skiers going down the mountain. And the resistance is the trees, the moguls, the narrow, icy patches on the trails that naturally slow the skiers down.
This is an exceptional way to explain it because it perfectly solves the hardest concept to grasp about parallel circuits. Let's start with a series circuit, though.
Okay, so a series circuit is a single, narrow cat-track trail winding all the way down the mountain. There's only one path.
Right.
Every single skier, all the current, must travel down this exact same trail.
Yeah.
So if a massive pine tree falls and blocks the path,
The circuit is broken, all flow stops completely, no skiers can reach the bottom.
it's just a massive traffic jam.
Yeah, this is the old string of holiday lights. One bulb burns out, and the entire string goes dark because the pathway is severed. Furthermore, every mogul and narrow patch on that single trail adds up. The resistance is cumulative.
So nobody designs modern houses with series circuits because if you turned off your TV, your refrigerator would lose power.
Exactly, that would be a disaster.
We use parallel circuits. So back to the mountain. A parallel circuit is when you reach the summit and you have, say, 5 different trails you can choose from. You can take the steep black diamond or the winding blue square.
Right, and here is where your mountain analogy really shines. What happens to the voltage, the elevation drop, in a parallel circuit?
It doesn't matter which trail you take, whether you bomb straight down the black diamond or meander down the blue square, you still drop the exact same total elevation from the summit to the lodge.
Exactly. The voltage drop is identical across every parallel branch.
That makes it so much easier to visualize.
But this raises an important question, though. If the voltage drop is the same, what happens to the skiers? The current?
Well, they split up, the crowd divides, more skiers will naturally take the easier trail, right? The path of least resistance.
Naturally.
The narrow, mogul-filled black diamond has high resistance, so fewer skiers take it. The current basically divides proportionally based on the resistance of each branch.
Exactly. And if an avalanche blocks one of the trails, the skiers just take the other 4. The overall flow continues.
Oh, that's why parallel circuits are so robust.
Yes, this is why you can turn off a lamp in your bedroom and the microwave in your kitchen stays on. They are on separate parallel branches of the house's circuit.
But then we get to compound circuits, which, if we follow the mountain analogy, is the entire ski resort taken as a whole.
Right, the big picture.
You might have a single trail from the summit, which is series, that suddenly splits into 3 different bowls, which is parallel, which then merge back into a single bridge over a road back to series. It's a massive interconnected web.
And this interconnected web is where things get intensely complicated for engineers. If you are designing a computer motherboard, you are building an incredibly complex compound circuit.
There's millions of tiny trails.
Yes, you are managing the traffic flow of billions of electrons through microscopic pathways.
Because they are all connected, a change in one place causes a ripple effect everywhere else.
Absolutely. If you add a massive mogul field, a high-resistance component, to one of those parallel bowls on the mountain, fewer skiers take that path.
Right, they'll avoid it.
They reroute to the other bowls. This changes the total volume of skiers hitting the single bridge at the bottom.
Wow.
In a circuit, changing a resistor on one parallel branch changes the total equivalent resistance of the entire system. That alters the total current being drawn from the battery, which changes the pressure, the voltage drops across all the other components in the series.
It's a massive domino effect. Without precise quantitative models, you'd never be able to predict what a microchip was going to do. You'd just fry everything instantly.
You would. You really need to calculate precisely how the current will split and merge across millions of junctions to ensure that one side path doesn't accidentally starve the main processor of power or, overwhelm a delicate memory module.
Okay, let's take a breath and look at the absolute journey we've just been on.
It's been a lot of ground covered.
We started with the invisible, foundational pushes and pulls of Coulomb's law. the intense atomic attraction and repulsion.
And we looked at how charges are never created or destroyed, just forcibly relocated, moved from the carpet to your shoe, or pushed to the far side of a metal sphere by the invisible peer pressure of induction.
Right. And then we took that static tension and we released it. We built the ski resort. We used the pressure of voltage to push a current of electrons through the atomic obstacle course of resistance, generating heat, light, and power.
All organized into incredible microscopic grids?
It is absolutely wild to think that the exact same physics explaining why a balloon sticks to a wall is the math keeping the global internet running.
These aren't just abstract ideas. You interact with these exact physical principles every single second of your life.
Every day.
They are the silent, perfectly predictable rules governing the neurons firing in your brain, the light switches you flip, and the battery keeping your phone alive.
It really changes how you look at the world around you. But I want to leave you with one last thing to ponder on your own, building on what we unpacked today.
Oh, let's hear it.
We talked about the absolute law of conservation of charge. In an isolated system, the total amount of charge never changes. It can't be created out of nothing, and it can't be destroyed into nothing. It just moves. It gets harvested, pushed, and pulled.
That's right. It is a fundamental constant.
Well, if the entire universe is essentially one giant isolated system, does that mean the very electrons flowing through the complex microscopic circuit of your headphones right now, generating the sound of our voices in your ears, have technically been circulating in one form or other since the literal dawn of the universe?
That is a staggering thought.
It really is. So the next time you reach for that doorknob in the winter and feel that little spark, just remember, it isn't a random prank. It's a mathematically perfect interaction involving tiny pieces of the universe that are quite literally as old as time itself, just stopping by to say hello.